Vinod, do you want to introduce her?
All right. Yeah. Thanks. So we are very happy to have Shweta again with us, though virtually. So Shweta is a professor at the CSE department, the IIT Madras. She did a PhD from UT Austin, but I guess also Stanford University. And she was a postdoc at UCLA. Then she was at IIT Delhi briefly before she moved to IIT Madras. Her area of research is cryptography, and recently her focus has been on post-quantum crypto. She has won many awards and honors, including the Swarna Jayanti Award, ACM India Award for Outstanding Contributions to Computing by a Woman, Best Paper Award at Eurocrypt, Google India Faculty Award, DY Award for Excellence in Research and Teaching. She has been invited at many prestigious conferences like Asia Crypt to speak, and Women in Mathematics. And she was also a program co-chair for Asia Crypt. And I should also add, she was our one of our Vigyan Vidushi keynote speakers a few years back. And you all remember, I'm sure many students would also remember the wonderful talk she gave. So this is like part 2, I guess. So Shweta, take it away.
Thanks a lot, Vinod. Thanks for the kind introduction. Thanks to Raghuvansh and all the organizing team for inviting me. I apologize for not being there in person. I really very much wanted to, but we have our interviews here, and I could not leave because of that. So anyway, we'll do this online, and hopefully I can come some other time. Before I begin, I'd like to tell everyone that please feel free to stop and ask me questions at any point. We'll keep this completely informal, and the more interactive, the better. Okay. So what I wanted to talk about today is a topic very, very dear to my heart. And this is what I like to call unlikely friendships, the fruitful interplay of cryptographic assumptions. Okay, let me tell you what I mean by that. So cryptography, is the art of secret keeping, as you might know. And even if you don't know much about cryptography, it's good enough if you just think of the basic notion of encryption. So this is something that everybody is familiar with. Yeah, you want to hide a message, so you encrypt it using the recipient's public key, and the recipient who has access to her private key can decrypt it, and no one else should be able to, right? So this idea everybody is familiar with. And now, being computer scientists, obviously we want to give some concrete mathematical guarantees for the security of any such system. And the sort of guarantee we give is via a reduction, right? So we show that, or we prove that breaking a crypto system is at least as hard as solving some difficult mathematical problem. Okay, so what we'll do is, we'll design this reduction, let's call it B. It takes the instance of some hard problem, right? Massages it into an instance of your crypto system, your encryption scheme, let us say. And now assume there is an attacker who can break this crypto system, right? And gives you this break. You will massage this break back into a solution to the original hard problem, right? So now, if you believe that this hard problem is hard, right? You believe that it should not be solvable efficiently, then that means that this attacker cannot exist, right? So this is the way we do it. And usually the security of any cryptographic scheme is based on the hardness of a single problem, right? So here, when I designed this reduction, usually the input hard problem here, there's just one of it, right? And this is very natural because, these hard problems, they live in some mathematical landscape. We'll see some examples. And these different mathematical structures and the sort of the computational hardness assumptions that we make on these mathematical structures, these are very different. So you're not expecting really for these to, mix with each other very well. So let's look at this via an example. Okay, so this is my favorite mathematical structure. This is a lattice. Now, the simplest lattice in n-dimensional space is simply the integer lattice. And you can apply a linear transformation to it and get another lattice. Okay, so a lattice is a discrete subgroup in Rn. And what you will do is you will take a bunch of basis vectors. This would be over the reals. And you take all integer linear combinations of them and you get some space that looks like this. So now this is of course a toy example in only 2 dimensions. In reality, we are interested in high dimensional lattices. Okay, so let's think of the dimension as 200 or something like that. And what are the sources of hardness on these lattices? So lattices are really, really amazing and beautiful. I mean, I could go on and on. They're very rich mathematical structure, very, very useful for cryptography. The problems that are hard on them tend to have a geometric flavor. Actually, that's why we don't know how to, quantum break them, because we don't know how to exploit this geometric structure. So what's a concrete example of a hard problem on a lattice? Well, the most famous one is this so-called shortest vector problem. Okay, so the problem is just as the name suggests. I have a high dimensional lattice. It's given to me as some set of basis vectors. And what I would like to find is, the shortest non-zero vector in this lattice. Okay, and in general, this problem is going to take me time, exponential in the dimension of the lattice. So this is an example of a hard problem. And now here's another very beloved mathematical structure in cryptography. It's an elliptic curve. So this is the equation for the elliptic curve. And all the points that satisfy this equation, right, they form a group, a cyclic group in our case. And the hard problem here is that if I give you a generator of this group, okay, let's call it G, and I raise it to X for some X, where X is a large high entropy value. So this high entropy will be important, right? Because if X is within the set 1, 2, 3, then given G and G to the X, I can figure out what X is. But if X is large and sort of chosen from some good distribution, then the so-called discrete logarithm problem says that it is hard for me to find X given G and G to the X. Okay, so these are 2 mathematical structures. And I hope you'll agree with me that, these really look very different, right? So, I mean, look at them. Like the lattice is infinite. This elliptic curve is over a finite field. I mean, by the way, I did cheat a little bit. So the elliptic curve actually looks like this, right? Because it's over a finite field. I mean, we're in computer science, everything is discrete. But other than the fact that it is discrete, they look very different. The hardness is very different. In lattices, it's a very geometric quantum hard, hopefully quantum.
So I have a question.
Yeah.
Suppose that the group was not cyclic and it had a generator set of size 2. Could we say that G to the X, H to the Y is also random in some way or hard, or no?
So suppose that the group is not cyclic and
But you have 2 elements that will generate all the others.
okay.
So let's say they are G and H. Can we say that G to the X and H to the Y it has the same property that you cannot, it is encoding X and Y?
Okay, good. Yeah, I mean, I don't know of any generic algorithm that will solve it even for that case.
Okay.
Yeah. So I think your question was, how important is the cyclic? Is that right?
Exactly. Yeah.
Yeah, I don't think it's very important. Actually, one of the things in cryptography is that, you're working with the structures on which the problems are believed hard. So here we have this cyclic group. I don't think it matters terribly, even if it is not cyclic.
Okay.
Okay, so what I was saying was, that this lattice problem has a really nice geometric flavor. It's an infinite mathematical structure. On the other hand, this elliptic curve over this finite field, I mean, it's a finite set of points. And the group operation is also very different, right? So on the lattice, for example, if I want to add 2 points, I just do the usual addition, right? Like you take two vectors, right? You put the head of one on the tail of the other, and then you draw the line. I mean, the usual addition that we do. On the elliptic curve, the addition is very fancy. So, if I want to add points P and Q, I draw a line through these 2 points. It intersects the curve on another point R. I reflect that point above the x-axis, and that's my P plus Q. So it's very different. My only goal in this slide is to give you a real taste of how different these objects seem to be. Yeah, so these are very different, and we don't expect really these two structures and these two hardness assumptions to have anything to do with each other. But what I'll show in this talk is that we actually found a way to get these two to collaborate to solve a long-standing problem in cryptography, and this is the problem of optimal broadcast encryption. So this was with Shweta Yamada when he was visiting IITM, and we received the Best Paper Award for solving this problem. So let me try to, set up the stage on what this problem is all about. So this is a very, neat, intuitive type of primitive, the primitive of broadcast encryption. And it's as the name suggests, okay? So it's an encryption scheme. But now I want to broadcast my information to a set of users. Okay, so think of something like Netflix. So, I want to stream a movie, let us say, and I have millions of users. And they have different subscription plans. So some are eligible to watch something, some for something else. More abstractly, right, here you have this content provider. And there are a whole bunch of users in the system, but she wants to broadcast her message to only some subset of users. Okay, so all that she has at her disposal is a broadcast channel. So it's the same sort of whatever she sends is going to be broadcast to everybody. And it should be the case that all the people that she has in mind, right? So only the sort of set that she encrypted to, they should be able to open and read this, and the others should not, right? And these others should not, even if they come together and try to pull together all their information and break things in some way, even in that situation they should not be able to. Is the notion clear? Yeah, sorry.
Yes, it's clear.
Okay, great. So yeah, so it's this broadcast based encryption scheme. And now what's a really simple way to achieve this broadcast encryption the way that I defined it so far? All I want to do is, send a ciphertext and it goes to everybody. The people that are authorized should be able to open the ciphertext. The others should not. So what's a trivial way to achieve this?
Use public keys of the people you want and concatenate those pieces.
Sorry. Yeah, exactly. So, just use public key encryption, right? So everybody agrees. I mean, it's very trivial to just use PKE. I mean, if I have these three users that I want to encrypt to, well, I just encrypt the message to each one individually. And the guarantee of public key encryption is that the bad guys don't manage to break this in any way, no matter what they do. So this is a solution, right? So the real question being asked in broadcast encryption is
Question?
Yeah.
So you send the same message to everyone, right?
Yes.
So whose public key do you use to encrypt it?
So
Out of the three?
here, this is just a play on, the same message to everyone. So what I'll do is I'll encrypt it one by one for each person. I'll concatenate everything, and that's my same message that I'm sending to everyone. Does that answer the question?
And how do they decrypt it? They can only decrypt. They only need to decrypt part of it.
Yeah, it's a redundant. It's perfectly redundant, right? It's the same message encrypted n times.
Okay.
So if I'm user number 10, right, I just throw away, all except my index, and I decrypt that. So this is why it's terribly inefficient.
Okay. Yeah. Thanks.
Okay, so the real question here that we're asking is whether a shorter ciphertext is possible. Now let's see what we know about this problem. So the trivial approach I already showed you, right? So here the master public key of the system. So, the public key that the encryptor would use, this is also order n because I need to have one public key per user. The ciphertext size is order 1, but the secret key is pretty short. So every user only has her secret key. Okay, so the secret key is short. This assumption that I can build this from is just plain good old PKE. Now, in 2005, there was a sort of really cool piece of work by Bonnet, Gentry, and Waters that showed how to use a bilinear map. I'll talk about what that is. It's related to our elliptic curve. Okay, so think of elliptic curves. Okay, so it uses certain types of elliptic curves to achieve much better parameters. So what they show is that you can actually trade off the size of the master public key with the size of the ciphertext as long as the product is root n. Product is n. So it could be n times 1 or root n times root n. It could be any n to the epsilon times n to the 1 minus epsilon. And they can achieve this. So this was sort of really a big step forward. And then there was no progress for a long time. And then Bonnet, Waters, and Zandri, all the way in 2014, showed that, actually it's possible to get optimal parameters. So here, when I say order 1, I'm sort of hiding, the polynomial factors in the security parameter. Okay, so this is just to keep the notation light. So these are optimal parameters. Okay, so everything is just, it doesn't depend on n, or you could think it depends logarithmically on n. But the assumption that they use is a very strong one. So they need to assume the existence of something called a multilinear map of high degree. And we don't actually have these in life so far, at least, unfortunately. I mean, it would be very cool to have this, but we don't. So this result is, mainly to be seen as an evidence for hardness. And what we showed is that actually you can get everything you want, but you need to use elliptic curves and lattices together somehow. Okay, so we'll see how to do that. Are there any questions so far? Okay, so how did we do this? So we observed first that, this primitive of broadcast encryption is closely related to another object called attribute-based encryption, which I will define next. So in attribute-based encryption, what you have is another generalization of public key encryption, where now you can have files. Okay, so you can have ciphertexts associated with access control policies. Okay, and the user's keys can now be associated with some set of attributes. So a little more abstractly, you can think of the ciphertext as having some function f built into it. Okay, the user's keys as having some input x built into it. And decryption will work only if the vector in the secret key satisfies the function in the ciphertext. Does that make sense? So just to remind ourselves again, okay, so now what we're going to have is that, see, typically, if I have a ciphertext, it is user by user, isn't it? So, for each of these users, I'll have one ciphertext. But in the real world, if you think about it, it doesn't really matter whether, it is Shweta or Meghna who's trying to decrypt. Typically, what matters is whether it's a faculty in computer science at IIT Madras, right? So, I mean, most data is encrypted against some sort of policy. So maybe, STCS, TIFR should be able to decrypt something, but CSIITM should not, right? And it does not really matter whether it's Vinod, Raghuvansh or Shweta who are trying to do the decryption. Usually the particular person is not important, but it's a role-based access. So now my secret key can have different attributes associated with it. That's why it's called attribute-based encryption. It could have, faculty, computer science, IIT Madras, right? Yours could have TIFR, STCS, and so on. And the file will have within it some access control policy. This policy, this formula will not be hidden. Only the contents of the file will be hidden. So think of some message M that's going to be hidden. And now if I, hit this ciphertext with my key, what will get computed is f of x, where x is in my key and f is in the ciphertext. And if f of x is 1, then, the box will open and the message will come out. Otherwise, it will not. So in this example also, if I pool together users and their keys, and they try to open a file that they are not individually authorized to, then they cannot, mix and match their keys or do anything else in order to open the file. So this is again collusion resistance in the same way that we saw in broadcast encryption.
So can we?
How is the function being presented as a circuit?
Yeah, very good question. So think of the function as a circuit.
In this case, can we think of f of x as the secret key? Is it identical or is there more to it?
What should I think of?
F of x as a secret key?
No. So let me see. Do I have? Okay, I don't have a slide for this, but no. So F is in the ciphertext. Okay, so the ciphertext is associated with some function F and some message M, where M is hidden. Okay, and the secret key is associated with some vector X from the domain of F.
Yeah.
So the secret key does not have F of X. The secret key only has X. The ciphertext has F. And this is important, right? Because I want the two to talk to each other, though they were generated separately. That is what is making it non-trivial. If the same party had both F and X, then it could just compute F of X itself. But here, the ciphertext or the encryptor has F, the key generator has X. So I'm going to compute a ciphertext with F in it. I'll compute a secret key with X in it. I'll bring them together. What will decryption do? It will compute F of X. And it open the locked box and reveal M only if F of X is 1.
Okay.
Is it clear now?
Yeah.
Okay. So, yeah, this notion that I've just described to you is called a ciphertext policy attribute-based encryption scheme. See, the main, the intuitive way to think about this is that, we are trying to generalize public key encryption, right? So public key encryption is user by user. But in the real world, access to encrypted data is not user by user, right? It depends on the roles that you satisfy. So against my encryption, I'm just going to specify what is the policy that should be satisfied for this file to be openable, right? And the secret key will embed those roles. And then if there's a match, then you can open. Okay. So this is a ciphertext policy ABE. And now if I reverse the roles of the, the key and the ciphertext, So now I put my function f in the key, and I put my attribute or my vector x in the ciphertext, then this is called key policy ABE. Okay?
Okay.
Yeah, so these are the only definitions that we'll need. Okay, so basically this notion of attribute-based encryption, right? And as I said, there are two variants of it. So either you can put the function in the ciphertext, or you can put the function in the key. You can do one of the two. Okay, so what we observed is that, if you have a ciphertext policy ABE, which has sort of some nice parameters, some sort of succinctness, which we'll see, then this gives us a broadcast encryption scheme. Okay, so this was observation 1. The second observation is that using lattices, we can actually construct this, CPABE scheme with the nice parameters we want. But this is not going to be collusion resistant. So, we talked a lot about this property of collusion resistance, right? Collusion resistance means that users cannot collude and break security of the scheme, right? So if I have two users whose keys don't work, any sort of clever combination of their keys also should not work. That there should be no way to leverage multiple keys to do anything. So what we showed is that using lattices, you can build something which is very nice algebraically. It satisfies the parameters you want, but it is not secure. It does not satisfy collusion resistance. Okay, and then what we showed is that we can use elliptic curves somehow to get this collusion resistance. Is this high level template clear? This is the recipe. Okay, so first we observe that this problem of broadcast encryption, you can recast it as a problem in attribute-based encryption, and you can build something which is not secure using lattices, and then you can somehow throw elliptic curves inside this to make it secure.
Okay.
Is there a question?
No.
Okay, so let's go a little deeper and look at our two assumptions. Okay, so first let's talk about, these elliptic curves. So what is the structure that we want and what is the hardness? So now, a little more concretely, we have these three groups, G1, G2, and GT. GT stands for G target. These are groups of, let's say, some prime order Q. And let's say little gi denotes the generator of capital GI. These are of order Q, right? So I'm going to pick some A and B randomly from ZQ. And these groups come equipped with a so-called bilinear map. Okay, so this map E, it goes from G1 cross G2 to GT. And it has the following very useful bilinearity property. So E of G1 to the A, G2 to the B is equal to E of G1, G2 to the AB, which is the same as GT to the AB. So you can do one multiplication in the exponent. Okay, so if I give you an element G1 to the A, and I give you another element G2 to the B, then I can apply this map to get A times B in the exponent. Okay, so I can do this quadratic computation. Now I showed you the multiplication, but addition anyway works, right? So in any group, I mean, I can always do, G1 to the A times G1 to the C, right? And that will be G1 to the A plus C. So, I mean, I can do one multiplication, and of course, I can do many additions in the exponent. So adding is not hard, right? So I can do quadratic computation in the exponent. I can do lots of additions and I can do one multiplication. And hardness, as I already told you, is that high entropy exponents are hidden. Okay, so I'm being deliberately loose about this. So, for the purposes of this talk, in fact, for the purposes of even doing research in the field, it suffices to just think that, anything that's sitting upstairs, as long as a trivial brute force doesn't work, right? Where I just compute GT to the 1, GT to the 2. I mean, the only way for me to recover the value of X for some G to the X should be G to the 1, G to the 2, G to the 3, and so on. I mean, there should be nothing smarter than brute force. So high entropy exponents are hidden. Are there any questions about this? Because this will be very important for us. Okay, so in the exponent of this group, you can compute quadratic polynomials over ZQ. And if you chose those elements, randomly with good entropy, right, then they will stay hidden. You will not be able to learn what they are when they are sitting in the exponent.
So what are the conditions for this bilinear map to exist? Does it exist for any G1, G2, G3 or?
No. That's a great question. No. It doesn't exist very easily. Actually, finding an efficiently computable bilinear map was a major breakthrough in cryptographic research in like the early 2000s or something. So there is a particular elliptic curve. There are a few, very carefully chosen, carefully designed elliptic curves where you can have this efficiently computable bilinear map. So they can exist also they can exist more often than they can be computed efficiently. So there are only a few well-chosen families of curves where you will have this. And when you have this hardness. You conjecture that you have this hardness, and it turns out to be super useful. Does that make
New hardness assumption. I mean,
what?
It's a new hardness assumption. This is not the discrete log. I mean, the normal discrete log hardness assumption, right? This is something new. I mean, it doesn't follow from this discrete log, right?
This is stronger than discrete log, absolutely. So for the purpose of this talk, I'm just really waving it under the rug. You can have different concrete hardness assumptions over these, pairings. These maps are called pairings. You can have different hardness assumptions, but the strongest hardness assumption, a sort of meta assumption that you can make, is that whatever is in the exponent, as long as it is high entropy, it remains hidden. So there is like a sort of meta assumption that one can make. And for the purpose of this talk, I'm just sticking with that high level idea. But you're absolutely right that this is not discrete log alone. I mean, if you could solve discrete log, you could certainly solve this, but the reverse doesn't hold. This is a stronger assumption.
Okay.
Yeah, great question. Any other questions? Okay, so the second assumption concretely is this learning with errors assumption. So this assumption effectively says that noisy linear products are computationally indistinguishable from random. Okay, so if I give you this tall matrix A and I compute, S times A and I perturb it with some noise, right? I get some vector. This distribution is conjectured to be indistinguishable from the uniform distribution over the appropriate dimension. Okay, so the details of this particular assumption are not very important. This is actually, more precisely the closest vector problem in disguise, but that itself relates to the shortest vector problem. So this is a classic problem in lattices. Okay, and this is what we'll use. So let's get deeper into it. So what we observed is that when you use lattices, they have excellent functionality. You can do a lot with it, but security is generally very tricky. And pairings, on the other hand, have very limited functionality, but security is fantastic. I'll tell you what I mean by this. Okay. So the learning with errors problem, for instance, many of you may know that, this is the only real assumption where we know how to build fully homomorphic encryption. And what is fully homomorphic encryption? It's basically public key encryption, but where you can actually compute on the data while it is encrypted. So I can, take my data, encrypt it, give it to some untrusted server who performs additions and multiplications, right? So computes some circuit on this encrypted data, gives it back to me, and I decrypt it and I get back what I want. So you can think that, encryption and function computation commute in some loose way. Okay, so this fully homomorphic encryption, you can build it using this learning with errors problem. And this is very expressive. You can support arbitrary circuits. It has really sort of short ciphertext, which is independent of the size of how big a circuit you compute on it. And the rule of thumb that I want you to take from this is that, you can do large degree computation. So you can use lattices to hide your data, your messages, right? You can encode them using lattices, and you can do lots of stuff with it. You can add, you can multiply again, add again, you can keep going, right? Any polynomial size circuit I can evaluate. But, security can be tricky. So for fully homomorphic encryption, it works. But for more advanced things, it turns out to be quite problematic. With pairings, the opposite actually holds. So the functionality is very limited. You can only do one multiplication. And this is already cool. I mean, you can do lots of stuff with one multiplication, but obviously it's nowhere close to homomorphic encryption. But the security is fantastic. So, forget this generic group, whatever I wrote, because I'm running out of time. But I just want to say that, once you put stuff up in the exponent, right? That's it. I mean, your life is made. You can do very little maybe, but whatever you do is secure. The adversary can learn very little. So the rule of thumb with pairings is that if you can somehow, whatever task you want to accomplish, if you can make it do with, degree 2, it's going to be secure. So, there's very little room to move, but whatever you can do will be secure. This is the rule of thumb. So it's really complementary. Okay, so lattice is great functionality. You can do a lot, but security is very tricky. Pairings, you can do very little, but it's very, very secure. So we hardly have any attacks. Okay, so our basic idea here is that, let's take the lattice samples which are over ZQ. So let's kind of just do this dumb thing of syntactically matching the space where the lattice samples live with the exponent space of these groups. Okay, so I told you, like, my group is, some finite, it has order Q. So, I can choose elements over ZQ. And now these elements over ZQ, they need not be actually random. They could be pseudo-random, right? They could be lattice samples. Right, so I'm just doing a very dumb thing right now. I'm just syntactically matching the spaces. Okay, so my LWE, as we saw, right, my LWE is this distribution, right? 1 distribution, 2 distribution, and it's just over ZQ. So it doesn't matter. I mean, whatever it is, it looks like something. Let's even forget what it looks like. I'm just going to say, well, it's a vector over ZQ. And this group I had, this order is also ZQ. So I'm just going to do this dumb thing where I take stuff from here and simply put it in the exponent over there. And this syntactically just works out, right? Just because, well, it's just ZQ. So, an obvious fact is that now I put my LWE stuff in the exponent of this group, right? My lattice samples, I put them in this exponent. And, a sort of dumb sort of conclusion I can draw is that, okay, I can do quadratic computation on the lattice samples. So note that sitting on the ground, I could have done lots of stuff with my lattices. But I put them in the exponent and now I'm stuck with a measly little degree 2. Okay, but I can do it. Certainly nothing stops me from doing it. And obviously the question you're asking is why, right? Why should I do it? And obviously the answer that we'll have, because we're having this talk, is that, we'll somehow manage to do the best of both worlds. Okay, so let's see how. So are there any questions?
No.
It's clear, right?
Yeah.
Okay, great. So let's, do step 1, which is where I told you that I want to cast my broadcast encryption question as an attribute-based encryption question. Okay, now this is, okay, it just works out. So basically, what was my broadcast encryption? The encryptor has to encrypt the message to some set S, right? Some set of users. So I'll just write down a circuit which has this set hard-coded in it. And remember, I wanted that users within that set should be able to open the ciphertext. So I'll just, take the user index and treat that as my vector, my attribute vector, right? So I'm just doing a very naive recasting of the problem. Absolutely simple. Okay. I'm just going to say that, okay, my attribute-based encryption, it seems like a very powerful thing. It can support arbitrary functions, at least the definition can. So I'm just going to do like a subset checking. Okay, so I have my set of legitimate users sitting in my circuit. And what will I do? I'll just take as input, different users index and check whether it's in the set or not. That's all. Okay. So I think this step is actually totally trivial. So, we're almost just restating the problem in a slightly different way. And the reason that we are doing it is that there exists prior work which will soon start becoming useful. Okay, so this is what the circuit looks like. So, is J equal to S1, S2, and so on. It will just check this. It'll output yes or no. Okay, very good. So we did almost nothing so far. Now, an observation is that this circuit that I wrote down has a short input, right? So it's just of size log n. Why? Because if I have n users, then, the index of the length of the index is obviously just log n, and that's going to be my input, right? The other thing is that, the depth of the circuit is also very short. It's just log n. But the width is big. The width is high, right? So, if I have S1, S2, and so on hard-coded in this circuit, then just checking one by one, I mean, a single check does not take time, right? It's just checking two vectors of size log n. But I have to do this n times. So, the width of the circuit is high. So here's another very obvious statement. If I had a CPABE scheme which had width independent parameters, okay? I just need width independence because everything else is anyway short. Then, this would be enough for me. Okay, great. But even without this constraint of succinctness width independence, it turns out that CPABE from lattices is a central open problem. So by the way, I mean, now we have some solutions. In fact, partly leading up from the work I'm presenting, but not from standard assumptions. Anyway, the point is that we don't know. Yeah, I think all I'm wanting to say is that we made this observation, so we reduced this problem to a different problem, which also we don't know how to solve, and we don't know how to solve this problem even without these constraints that we have of width independence and so on. But it turns out that if you look at the dual of it, right, the key policy version of this attribute-based encryption scheme, then actually there's a solution which has width independence. Okay, so in key policy, remember, the secret key is associated with some function f. The ciphertext is associated with some input x, right? And what I want is, that everything should be independent of the width W of the circuit. And it turns out I get this. But the problem is that this X and F are in opposite order. So what I wanted is, I wanted CT with F and SK with X. But what I have is only this. Okay, so I have CT with X and SK with F. I don't know, just seeing a talk about it, maybe this doesn't seem like a very big issue, but this is a very big issue. So, it's very hard you cannot just easily swap them. And yeah, I mean, so KPABE, the one where, the key policy. So the key has the policy F, right? This is easy to build, at least in hindsight. But the ciphertext policy version, where the X and F would be swapped, this is very hard to build. It remains very hard to build, even though we have some progress now, but a full solution is still not known, even in 2024. So here's a question. Well, can I use what I have? Okay, so I have this KPABE, can I use it? So now here are some ideas. Okay, now we're going to use some very nice algebraic structure that, this key policy scheme has. The first one is decomposability. Okay, so what this means is that if I want to encrypt a vector X, okay, of length L, then what I can do is I can encrypt it bit by bit. This is basically what it means. Okay, so for the first position being both 0 and 1, I can generate an encoding, right? So C10 means if the first position of my X is 0, then I'll use this. If the first position is 1, I'll use this. If the ith position is 0, I'll use this. If the ith position is 1, I'll use this, and so on. And when I know X, right, I will simply pick the correct one. So for the all zeros X, I'll just pick the the top row, and so on, right? So decomposability just means that, I can encrypt bit by bit. And this is actually a very powerful algebraic property, because it allows you to somehow compress 2 to the L things into 2 times L encodings, right? So if I forget for a second about any security or anything, think about what this slide is saying, right? It's saying that any value of X, any of the 2 to the L values of X, any of them can be encoded using this, 2 times L matrix. I just have to pick the encodings. Does that make sense? Yeah, great. So that's great. Okay, so what could I hope to do? Okay, now remember, I'm trying to create an encryption for some formula F. Okay, what will I do? Well, let me, sample an ABE scheme, the one that I know how to sample. So the key policy one. And remember, I told you that, in this scheme, I have to put F in the secret key, right? Because again, that's all I know how to do. So my encryptor is just going to sort of sample the scheme, put the function where it knows to put the function, and it will simply give, the ciphertext for all possible X. Because I'm the encryptor, I only know F. I have no idea what the X is that you want. Yeah? Question?
No.
Okay, so I don't know what X you want. I want to support all possible X. And we saw in the previous slide, there's a way to support all possible X. Just using polynomial blow up, right? Using this one little matrix, I can support exponentially many X. So, I could certainly give you this. But of course, as you can imagine, this is not going to be secure. So, if I give you only one entry per column, it's okay. But if I give you 2 entries in any column, then you're dead. Okay. And it turns out there's a simple linear attack that I can mount in order to kind of break open your lattice and learn whatever I want to. So here's another idea. Let me just throw public key encryption on top. So now what will I do? I'll give you 2L PKE schemes. Okay. And every entry in this matrix, right, I'll encrypt with that particular public key. So I'm just saying that, okay, you don't want to learn both entries in each column. So let me encrypt all of them with different keys, and whichever X you have, right, I'll give you the secret keys for just those entries. So for the all 0 value of X, I'll give you all the top secret keys. So now what happens? You take these, right? You open the legitimate ones. The rest of them you can't open because you don't have the public keys. Okay, and the rest of it works as before. Yeah, but now, well, if I even have 2 users, right, who have mutually exclusive keys, then basically between them, they have all possible secret keys. They can open everything and all bets are off again. Okay, so the main new idea that we tried here is to use pairings in place of public key encryption. Okay, so yeah, I already told you. I'm just going to do this silly little thing of putting these encodings, right? So I told you I have these, these nice encodings. These are all lattice encodings. I'm just going to put them in the exponent. Okay. I'll just put them all in the exponent and I'll somehow hope for good things to happen. Now let's look at, the challenges one by one. Okay, so the first thing is, how do I prevent collusion attacks? Because when I was not using pairings, when I was using only public key encryption, that was the problem I was running into, right? That you and I could pull together our keys and get more than what we should be allowed to. So what we'll do now is we'll randomize keys for each user U with a fresh randomness. Okay, so what we'll somehow do is we'll allow the decryptor to recover some delta U times CIXI in the exponent. So this bracket notation means that it's sitting in the exponent. Okay, this bracket sub T means it's just to make the font bigger. Okay, so this is sitting in the exponent. Now, if I have 2 different users, right, you and I try to combine our keys, well, there's a randomness that prevents us from combining them. So you have delta U prime, I have delta U, they don't cancel. So I know this is very vague, but yeah, it's because of time. So fine, we can't do anything. Okay, so good. So now I told you that, I'll prevent these collusion attacks by doing some sort of extra randomization. Now I need it to be the case that, you can only select one out of two encodings, right? So how do I do that? So in the public key, I give you, remember previously I was giving you a whole bunch of public keys, right? I'm giving you something similar. So I'm giving you sort of position-wise randomness in the exponent as the public key. Okay. And the ciphertext is now going to have these encodings. Each of them will be multiplied with the correct positional randomness here. Okay, so remember there is a randomization we are doing in the key.
Hello. You're muted.
Shweta, you're muted.
Now can you hear me?
Yes, yeah.
So did you hear this part where I was saying we'll cancel out exactly one of the two random terms?
No. I think the last thing we heard was when you're talking about MPK.
Okay. So what I was saying was that in the MPK, I have these 2L random things in the exponent. Okay. So remember that the square bracket means in the exponent. Now the ciphertext is going to give me the lattice encodings in the exponent multiplied by whatever is in this, MPK, this public value, right? So remember, I have G to the W10. I compute C10 and then I simply multiply it in the exponent, right? I can do that, right? So I just do G to the W10 to the C10. So I get G to the W10, C10. And I compute all these terms in this way. And in the secret key, what I do is I give you a cancelling term for only one out of the two entries. So I cancel out the randomness, right? Only for one. So you look at this term and this term. Now, if I compute my pairing, I multiply these two, right? These red terms will die, right? And I will just get this delta times CI, which is what I wanted. So far what I did is I randomized the key somehow, right, for getting collusion resistance. And I selected one out of two encodings. Now, so far, I would say, this is not super surprising because randomizing was like a linear type of a thing, which I could do using a pairing. Selecting one out of two also, it feels like a quadratic operation, right? I can do that using a pairing. But the whole question I'm trying to solve is computing the set membership, right? I want to figure out whether that index is within the set S. So this set membership computation is actually in NC1. But now I'm sitting in the exponent and I told you I can only do quadratic things there, right? So how am I going to hope to do this, right? So why should this be possible? And this was really sort of the beautiful serendipity of this technique, is that it turns out that, this when I want to compute this set membership on the lattice encodings, the algorithm that I have to do that can be restructured in such a way that the non-linear part of it is actually, it's something which can be done publicly downstairs. And the only part which has to be computed on the secrets is linear and can be done in the exponent. So basically, this really sort of serendipitous structure of this, membership testing algorithm allows you to compute an NC1 circuit even in the exponent. Okay, and using this, user-wise randomness, we managed to prevent the collusion attacks that were plaguing us on the ground. So you see what we did? I mean, we knew how to do it on the ground in an insecure way. We simply put it in the exponent and randomized it in 2 dimensions. So one with the position-wise randomness and one with each user's key. We found a way to cancel the position-wise randomness using the pairing. And we found a way to handle, I mean, the user-wise randomness allows us to prevent the mix and match attacks or the collusion attacks. And we somehow managed to compute the set membership testing in the exponent itself. Okay. And yeah, I mean, I do have a few more details, but I can see I'm out of time. So we'll not go there. Instead, let me kind of zoom out and look at the ideas that came together. Okay, so the first thing was decomposability. Okay, so I managed to compress 2 to the L values of X into, just order L encoding. So that was the first thing that helped us. Then we wanted to select 1 out of 2 in each column, right? Depending on the secret key. So what we did was, well, we moved upstairs. We randomized afresh for each key. This prevented us from having collusion attacks. Then we randomized separately for each row and column and used pairings to select 1 out of 2 in each column. Okay, then we restructured the set membership computation in the exponent so that the private part is linear and can be computed even in the exponent, even though, so it's very strange in some sense, right? You can only do quadratic computation, but because it is already encoded within a lattice, you can restructure the computation so that the heavy part of the computation can be done downstairs. Okay, so you see how lattices are helping. I mean, you would imagine that if I'm putting something in the exponent, I'm doing a nesting, right? I'm nesting it within lattices and then I'm putting it in the exponent. So you would imagine that functionality wise, this should only hurt me because I'm encrypting twice. But actually it helps you because it allows you to do deeper computation that you could have done if you simply had the values in the clear in the exponent. Okay, now I also need to decrypt upstairs, which I didn't have time to show you. And it turns out there's another really amazingly, serendipitous thing which happens, which is that what you get in the exponent is actually noisy. But it turns out that you can also restructure the computation in a way that you can bound the noise growth for NC1. So it won't work for all of P, but it will work for NC1 and that suffices for broadcast encryption. So there were a lot of very happy coincidences that, came together. And yeah, I don't know, it just wanted to work, it was like every issue wanted to be resolved. So the algebraic structure of these things was set up in such a nice way, all by chance, or whatever you call it. But I mean, not engineered to work together, but these 2 completely different objects, these elliptic curves, these lattices, they somehow wanted to make this thing work. And everybody satisfied what was needed in order to kind of, cross hurdle after hurdle. So yeah, basically it works out. Now, this technique helped the community get unstuck on other important problems. The most important one, I would say, is this one, which actually finds a way to emulate what we were doing with parents. This work finds a way to kind of propose a new lattice-based assumption, a very strong one, but nevertheless, an on-the-ground assumption that allows you to emulate the functionality that pairings was giving us. So this, I think, has been really important because it's helped us to do many other things which we were stuck on for a long time. So, for instance, we managed to do multi-input attribute-based encryption. This is something that we did, with our PhD student. And then, there were a couple of other things that, we didn't know how to do before, which also we did. And just as of last week, I mean, just at this upcoming crypto, so the same technique, building upon this follow-up work, which doesn't get stuck with degree 2, but kind of finds a way to bring it downstairs. We managed to do attribute-based encryption for Turing machines rather than circuits, and this has also been open for a long time. So again, it's sort of the same new lattice tools that emerged out of this approach. So to conclude, by the way, there are a few other really fantastic examples of this kind of collaboration between structures, which I don't have time to get into. But I'll be very happy to talk to anyone who wants to learn more about this. So to conclude, sometimes mathematical structures and hardness assumptions can collaborate to wonderful effect. It's often surprising, but whenever it can happen, which is few and far between, admittedly, but it can lead to progress on important open problems. What I really love is, like in this line of work, later this collaboration actually, proved to be redundant. So later, I mean, the community found a way to replace pairings with a pairing like lattice structure in some sense, right? So everything moved to the ground, and actually that became very powerful because you got the security you wanted, but you were not stuck with degree 2, so you could do a lot more. And I think a really fascinating topic of research, which I actively work on, is to find more examples of this phenomena. So I'll stop with that, and I'm happy to take any questions.
So why is AV for Turing machines harder? You can just convert it into a circuit, right?
Yeah, good. So yeah, it's harder because you want to support unbounded input length. So in a circuit, the input length will be fixed, right? But for a Turing machine, the input length need not be fixed. So you would like to support that. The other thing you would like to support is input specific running time. So in a circuit, the circuit will sort of unroll the whole computation of the Turing machine. So every input you will take the same amount of time. But in Turing machines, for different inputs, you can run in different times, and that's what you would like to support. So one very basic hurdle in supporting Turing machines, well, there are several, but one of them is that you don't know how to support unbounded depth circuits. Like a Turing machine, if I represent it as a circuit, right, I don't know how long the computation will run. So I'll have to, if I want to make it a circuit, I'll have to fix the depth of the circuit. But I want to support unbounded depth, unbounded input length, input specific running time, and that turns out to be quite hard to support. Does that answer your question?
What other NC1 problems have this structure of where the hard part is downstairs and the top part?
This is the only place I have seen it. It's like I said, it just wanted to work for you. So I haven't seen this anywhere else. Basically, what happens is that because you put it inside the encoding, the lattice encoding, you manage to restructure the computation so that the public thing is the heavy part.
Okay.
Yeah. It's very specific to that particular way of computing on the encodings. It's not generic. It's very highly specific.
More questions? Okay, so let's thank Shweta again.
Thank you.
Thanks, Shweta.
It's a very engaging thought. I really like it.
Thanks. Was it clear?
Yeah. Yeah.
Great. Awesome. Yeah, I thought that it's broad, like it's about this theme. And there are other really cool examples, so I love this because like I'm in ACM India and I'm the chairperson for diversity and inclusion. And I feel like, this is diversity and inclusion in cryptography, like, where everybody brings something beautiful and valuable, right? And you want them to talk to each other.
But for that, you have to change the last slide where you say one of them is redundant.
I know, but sadly, that's true. That's true. It doesn't go with the DEI story. But yeah, I mean, mathematically speaking, I think that this has happened a few times. And in this particular case, I think it's been super effective because this new assumption that came out following our work, right, where this pairing thing kind of got replaced by a similar strong assumption on lattices themselves. I really love this work because we can do so many new things with it, which were not known before, and which were not only were not known before, but which we had tried for many, many years. Like this ABA for Turing machines is a problem I have worked on since my postdoc. So this is a long time ago. Let's not go into how long, but I mean, I worked on this problem for so many years, and now it just wanted to work. It was one afternoon and it worked out. So it really shows, I mean, the community, like the ideas, everybody, has such a different way of looking at it. Like we were thinking of pairings, and then, this follow-up paper had this beautiful way of moving back to lattices. And now that has proved so powerful, right? So now, we've made progress on so many new things
But,
of that.
but you said that when you go back to lattices, the assumption is not standard. Is there, or is it still?
This is a very current area of research. It's not standard, it's true. But I mean, what's a standard assumption? Like, give it a few years and we can call it standard. So with crypto, everything is on the waves anyway, right?
Yeah. Okay. Yeah. Thanks for agreeing to speak here. Hope we can have you again.
Thanks again for
No.
inviting me. And we know you're saying something.
No, it's good seeing you. We hope next time we'll see you in person.
Sorry?
No, I hope next time we'll see you here in person.
Yeah, even this time actually. So we had scheduled it earlier. I think
Oh, yeah, I saw you
moved
you
it.
give a talk. Yeah.
Yeah, then we moved it. And when we moved it to today, I thought I would come in person. But
Get the interview.
how
Yeah.
it is with these interview dates, right? So yeah, they came on the same week, and then I thought that I should help out with that. So, and I didn't want to, I actually went and checked your calendar that, weeks around this week were already taken. So I thought it would be too complicated to reschedule like from scratch again. So yeah, but another time.
Yes. All right.
Okay.
Thanks.
Thanks again for having me.
Bye.
Bye, Raghuvansh. Can I see you once?
Oh yeah. Sorry. Yeah. Hello.
Oh, there you are. Hi, good seeing you. Long time. How
Yeah. Now I can see because now I'm set.
Sorry?
Now I can see you because I'm on this side now.
Oh, I see. Okay, well, how have you been?
Pretty good. Yeah, I'm liking it here. I joined last July, so it's almost a year. I'm liking it so far.
Wonderful. Yeah, you should come visit.
Definitely.
Absolutely, we'll make it happen.
Yep.
Okay, great. Okay, bye.
Bye.